All right, hey there, class. We're here to look at part B of our example 5. If you missed out on the first part of this problem, you're going to want to check out the other video that talks a little bit about how we did part A. So I want to make a note here that in part B, we do have the same force that continues to push the block after it starts sliding. So I do want to kind of bring up our free body diagram here that we had kind of discussed. Basically, at this point in time, we still have these same four forces. All right, now the magnitudes may be a little different. In fact, that is the case. The force of friction for this part B will actually decrease by a slight amount, and that's because the kinetic friction coefficient here, or sliding friction coefficient, is less. So it's going to reduce from the 0.7 to 0.5, which will in turn reduce the amount of friction that's acting here. So, as a result of this frictional force decreasing, we will no longer have a situation of equilibrium, and it will begin to accelerate to the right as it does that. So, I do want to bring back what we did in the implementation in that part of the problem. The same net force equation still applies. This simplification that we made over here, substitution of zero acceleration, no longer applies. All right, so this is the important distinction in part B. We can no longer say the acceleration is zero. So therefore, these two forces are no longer balanced in magnitude. So basically, I'm going to pick up with this problem here. I'm going to pause, I'm going to write some stuff down, and we're going to pick up with this problem right here. Okay, so here we are. I did a little write-up. Basically, my strategy is to write the net force equation to be able to find the acceleration. And since the acceleration is in the x direction, it makes sense, or hopefully it makes sense, that we're writing the free body diagram for the x direction. So I have the two forces acting on the object, the applied force and the force of friction. They're going to equal the mass times the acceleration. Solving this for acceleration, I end up dividing the m to the other side. Now the problem here is if I think about what I know, I only know the applied force and the mass. I don't have the force of friction yet. So very similar to what we did before. To find the force of friction, we're going to substitute in mu Fn into this equation. I do notice here that my mass should be divided over. That's a mistake. I did that in the last step. Forgot to write it here, so whoops, that's not an eraser. Let's just fix that up. So this should be the acceleration, and then the mass is divided right there. Continuing on, I notice here that in the y direction is where I'm going to have to find my normal force, because again, the normal force is in the up and down direction, the y direction. So I write that net force equation. And because it's not accelerating up and down, then my acceleration here is zero. Like in the previous part of this problem, these two things are equal in magnitude, opposite in direction. And ultimately, the force of gravity, if I make this substitution here, I am going to find that the normal force is equal to mass times gravity. As I get down into my last step here, I have the normal force substituted in here. I have all of this solved for A, and basically now it's just a matter of substituting in some values. Now, I do want to point out there's a bit of a red flag here. Okay, specifically, the red flag has to do with the sign that you're seeing here. Now the issue is that when we substitute in here to the equation, this is a magnitude substitution. Okay, it's not really a vector substitution. If you think about the force of friction, in fact, let me zoom out to my free body diagram here. If you think about the substitution, this is a negative direction force. So in the end, that really is subtracting from our problem. So the red flag here is even though our equation tells us to add these together, you're adding together a negative force. So I'm going to say, I need an eraser, I'm going to say that what we're going to do to fix this is we're going to actually subtract these two. So let's put the numbers in. The applied force from the previous section was 343, and that was in a positive direction. We're going to have, this is sliding now, so the coefficient of friction is 0.5. The mass is still 50 kilograms, and gravity is still 9.8 newtons per kilogram. Divide that all by mass, and that is going to equal the acceleration in the x direction. If you do this in your calculator, you will see that you're going to get a magnitude of 1.96 meters per second squared in the positive direction. And this will be the acceleration that will occur if that constant force from the previous section maintains. So this is what I would say our response is.